We're now going to have a look at how we express very, very large numbers and very, very small numbers in a shortened form called index notation. So numbers can be expressed in index notation. Now, index actually means the same as exponent, which means as a power of 10. For example, we have this large number here and this small number here. So how can we write each of these in a shortened form? Well, what we do first, we write out the two numbers that are given, non-zero numbers, which are 3 and 5, and we put the decimal point after the first non-zero figure, which is 3. So we write 3.5. Now, it needs to be expressed as a power of 10, so times 10 to a particular power or to a particular index. Now, to work out what this index is, we put the decimal point after the first non-zero figure, which is 3, and then we count. And we move to the right. We count the number of digits after the decimal point. We go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 3.5 times 10 to the power of 11. Now let's have a look at the next one. Now this is a very small number. Again, we follow the same idea. The non-zero digits that are given are 1 and 2. So we write now, the decimal point goes after the first non-zero figure, so it is 1.2, it comes after the 1. Expressing this in a shortened form, in other words, as a power of 10, so times 10 to a particular power. Now what will it be? Now there's the standard position of our decimal point. Now this time, when we count, we move to the left and we go 1, 2, 3, 4, 5, 6. And there's our decimal point there. So it is 1.2 times 10 to the negative 6. Now why negative? Because we had to move to the left to get to our decimal point. Also too, you can see that this number is a very small number. So it makes sense that this power here is negative. Now this is very convenient since very large numbers can be expressed in a shorter form. Now here's another example. We have the mass of the Earth. This very large number here, the mass of the Earth there in kilograms. Now often when we express a very large number, to make it easier to count, it's advisable to express the number in groups of 3, where the digits are in groups of 3 there. And it makes it much easier to count. Now here we have the first non-zero digit is 5. So the decimal point comes after the 5 and we write 5.98. Times 10. Now let's count the number of digits that are after the decimal point here. Now this is easy to count because how many digits are there? Well, as you can see, they are all in groups of 3. So how many groups of 3 are there after this decimal point here? Let's count. There's 1, 2, 3, 4, 5, 6, 7, 8 groups of 3. 8 times 3, 24. So the mass of the Earth is 5.98 times 10 to the power of 24. Now to express a number in index notation, we must move the decimal point to the standard position, which is after the first non-zero figure. Then we count the number of digits away from the standard decimal point position. This number represents the index to base 10. Now, if the decimal point is moved to the right, as we did here, you can see we move to the right here. The index will be positive. You see the index was positive. If the decimal point is moved to the left, for example, here, we move to the left, the index will be negative. You can see the index was negative. Okay, let's do this example. Express the following in index notation. Here we have 1 million. So there is the standard position of the decimal point after the first non-zero figure. So we write 1.0 times 10, and now we count 1, 2, 3, 4, 5, 6. So times 10 to the 6. Now, we don't, in this particular case, because we have 1.0 here, we can just simply write that as just 10 to the 6. It's just as easiest. Next one here, part B. Okay, this time now, same thing. We write 2.5, so we put the decimal after the first non-zero figure, times 10, and now we count 1, 2, 3, 4, 5, 6, 7, so times 10 to the power of 7. Now, as you can see in both cases here, parts A and part B, we moved the decimal point to the right, so of course we have a positive exponent there, or index. Now let's have a look at part C here. Now this is a small number, so we would expect therefore to have a negative index. That makes sense. Now there is the first non-zero figure, there it's 3, so we write now 3.0 times 10. Now this time there's the standard position of our decimal point. We have to move to the left. 1, 2, 3, 4, 5. Now because we move to the left, the power will be negative 5. Here part D, we have 1.25. So the first non-zero digit is 1 there. So there's the decimal point. So times 10. Now again, let's count. We are there. So we count to the left now. 1, 2, 3, 4, 5, 6, 7. So times 10 to the negative 7. Again, negative because we had to move to the left. And also, as you can see, this is a very small number. 100, well, you know that's 10 to the power of 2. We can just write it like that. And now number F here, well, again, there's the standard position of our decimal point. We go 1, 2, 3 to the left. So I can just write 10 to the power of negative 3. And that's how we express very large numbers or very small numbers in shortened form by using index notation.